I'm Shalabh. I'm a postdoc at ICTS in the Astro group, and my expertise is in numerical relativity. And instead of going into detail what I have been doing so far, I will just give a broad overview of my field of research. So the title of my talk is Spherical Einstein field equations on hyperboloidal slices. So by spherical Einstein field equations, I just mean Einstein field equations in spherical symmetry. The full 3D is kept for the near future once we finish it, and we are about to finish it. And as I go along the talk, I will introduce what hyperboloidal slices are. So before I proceed, I thank all the organizers for letting me present my work in the event. And I have been doing this work in collaboration with my friends. Akash, Ines, and Christian are the PhD students. Miguel, Alex, and Edgar are the postdocs, and David, Prayush, and Vishal are the faculties. All of you might know Akash, Prayush, and Vishal because they are the native people. Ines is in Valencia, and rest of the people are in Lisbon. So, first of all, I need to introduce why numerical relativity is important, why this field of research is important. Ultimate objective is to do astronomy of any faraway astrophysical process, not only via the electromagnetic radiations, but also associated neutrino counterparts or gravitational wave counterparts. All these processes combined introduce a field which we call multi-messenger astronomy. But the problem is that most of these processes are governed by a set of very complicated equations, which also involve the Einstein field equations. And for a general setup, we don't know how to solve these equations at all. Simply because they are a system of coupled nonlinear partial differential equations. And what do I mean by a general setup? So by general setup, I mean that by any given initial data or initial conditions, I don't know how to find the general solution. So we need to invoke the numerical methods. In the present state of the art, we cannot do better than that. So the ultimate aim of numerical relativity is to evolve any initial data, which may also involve any initial matter distribution using the Einstein field equations and the equations governing the dynamics of matter to any desired degree of accuracy and any amount of time we need. And as we do it, as we evolve the system, we extract the gravitational wave signal at fusion null infinity. So first of all, what is fusion null infinity and why is it important? So fusion null infinity is just the infinite future of all the outgoing light rays or null rays. And why is it important? Because it is the only region where we can define the gravitational waves unambiguously. By unambiguous, I mean that independent of the choice of gauge or coordinates, or etc. The general definition of sky plus is far complicated for like any initial given initial data, because the outgoing light ray null trajectories are also a solution of the Einstein field equations. But again, the physical definition still holds. It is the infinite future of all the outgoing null rays. But we can understand them in Minkowski spacetime because of this reason, because this is the simplest form of spacetime we can have, the trivial solution of the vacuum Einstein field equations. So if we consider Minkowski spacetime in spherical polar coordinates, this is how the metric looks like, where t and r are the physical time and radial coordinates. Time take all the real values and radial coordinate is always non-negative. From these coordinates, we can define ingoing and outgoing null coordinates, which we denote by big U and big V. And this is how the metric looks like. And from the definition, we can see that this is the domain of dependence of big U and big V, and V is always greater than or equal to U. So as big T goes to plus or minus infinity, keeping the radial coordinate constant, we reach future or past time like infinity. Or if we keep our time coordinate fixed and take radial coordinate infinite, we reach spatial infinity. Similarly, when we keep our ingoing null coordinate U fixed and take V going to plus infinity, we reach the future null infinity, which we denote by sky plus or script I plus. And similarly, as we keep V constant and take U going to minus infinity, which we reach past null infinity. But now you might be asking, okay, so all these definitions, they consist of infinite values of the coordinates, but in general we have like limited resources, limited computational resources, and so finite computational grid. how can we like map these coordinates to our finite. So one solution is using the compactified coordinates. So one example was given by Penrose by just introducing compactified null coordinates, which we denote by small u and small v, and they're defined as the tan inverse or arc tan of big U and arc tan of big V. And in terms of these compactified null coordinates, this is the form metric takes. So in this form we can see that all the quantities in the bracket have a nice regular form, so they are of order 1. But this coefficient which sits outside this metric, I mean outside these terms, takes infinite values as u or v go to plus or minus pi by 2. So to regularize this, we introduce a new metric which we call the conformal metric, which we define like this, and big omega is just twice of cos u and cos v. And as we can see that this conformal metric is well behaved, regular at all points, and this is the domain of dependence of small u and small v. So again, because of this condition, small u is always smaller than or equal to small v, and they take values from minus pi by 2 to plus pi by 2. So using these compactified null coordinates, this is how we map the entire space-time on a finite region. So basically this triangle, and which we call it the Penrose diagram of Minkowski space-time. So in this diagram, the future and past time-like infinities are sit here at these 2 points, and which we denote by I plus and I minus. I0 denotes the spatial infinity or space-like infinity, and this whole region is the future null infinity, and this whole region is the past null infinity. So as you can see that we actually compactified the null coordinates, so which means that the null directions still remain the same, but the price we pay is that the constant time surfaces look like this, the solid lines, and the constant radial coordinates look like these dashed lines. These are the examples, these solid lines are the examples of Cauchy slices. After introducing this compactification, this is how the problem of mapping future null infinity or square plus on a finite computation grid looks like. So this problem needs to be solved at all 3 levels: geometric, analytic, and numerical. So at the geometric level, we solve this problem by introducing a foliation or slicing of spacetime in terms of 3-dimensional hypersurfaces, which facilitate mapping of square plus at a finite numerical grid. And the analytic part of the problem consists of solving it, defining a well-posed formulation of Einstein field equation. And what does well-posedness mean? So an initial value problem is called well-posed if there exists a solution which depends uniquely and continuously on the initial data. And at the numerical front, this problem is solved by deriving a discretization scheme that preserves this well-posed formulation even at the discrete level. But the problem is that all the existing methods have limitations at least one of these levels. So for this we introduce hyperboloidal slices which look like this. So they are space-like everywhere, but they meet the future null infinity, unlike the Cauchy slices which meet the spatial infinity. So basically, if we define our grid along these surfaces, we can map square plus on a finite computational grid. And along these curves or hypersurfaces, we define a compactified radial coordinate which we denote by small r. So basically, small r in our case takes value from 0 to 1, as big R goes from 0 to infinity. And the level sets of these slices define a function which we call the hyperboloidal time, which is denoted by small t. So basically, this is how we solve the problem at the geometric level. At the analytic level, this problem gets reduced to defining a well-posed formulation of these equations on hyperboloidal slices. And this is achieved by working in generalized harmonic gauge. And why this gauge? Because these equations have been proved to be well-behaved, well-posed by several authors in this gauge. And the first one was Ivan Choke-Bruja in our seminal paper in 1952. Maybe many of you might know that she recently turned 100, and just to celebrate that, we at ICTS and RRI celebrated her centenary year in form of via a conference, which I think. So I circulated the advertisement, basically. And at the numerical front, we solve this problem by introducing a scheme which we call summation by parts, which proves stability for a class of linear equation on a broad class of slices. And when we combine all these three ingredients, this is how the solution looks like. So x-axis is the compactified radial coordinate going from 0 to 1, and y-axis is just amplitude of various dynamical variables. So which are denoted by this c plus c minus delta epsilon. You don't need to worry about what are these variables. So they come from the metric components, and this simulation shows that how an initial data given at t equals 0 evolves with time, and all of it leaks through square plus. So these are the vacuum Einstein field equations, and here the simulations for the Einstein field equations with matter. We have matter is a scalar field satisfying the linear wave equation. And so these are the results, summary and conclusion. So NR, I hope I convinced you that is presently an indispensable ingredient of gravitational wave astronomy, and the accurate predictions of gravitational wave signal require including square plus in the computational domain. And hyperboloidal slices promise solving the problem at all these three levels, and we give prescription how this can be solved, and we obtain some promising results. So for more details, I am here. You can catch me. Thank you for your attention.
So question. So here you had a scalar with some. What is the initial state that we are looking at?
So okay, in these simulations, we just gave a Gaussian initial condition to scalar field as well as to all the dynamical variables. We did not care about constraints. Actually, we solved the constraint equations, but because I did not have enough time to run the simulation and produce the data, so I did not show it.
But the initial state is spherically symmetric, or
no, yeah, it is completely spherically symmetric. Initial data as well as all the equations, all in spherical symmetry.
Okay.
Any other question? Why are some of the variables saturating to a positive value at infinity?
Okay, because they have a sharper fall off rate. So we rescaled all the variables by single power of r. Some of them fall off like double powers of r, like r square. So that's why they go to 0 at square plus.
Going to 0 was what I expected for all of them. Why are some of them not going to 0?
Okay, because some of the variables, I mean, they are of order 1 even at square plus. They are of order 1 even at square plus.
Okay, so let's thank Shalabh for his talk.